Okay. So, we are discussing as to why the classical diffusion equation fails to describe spinodal decomposition. What we showed is the following. We have the classical diffusion equation which is written in terms of mobility looks like this, dou C by dou T is equal to m by n v g double prime del squared C by del x squared, right. Because m by n v times g double prime is nothing but the diffusivity. Okay, so, this is the classical diffusion equation we have. We showed that if you use this diffusion equation in regions where g double prime becomes less than 0, this equation predicts ordering, right. This equation predicts the following type of structure. What is the structure? Instead of predicting phase separation, what happens in phase separation? In phase separation you have all these atoms phase separated. So, you have all A atoms on one side, all B atoms on side, but you are here you are having alternate AB atoms. This solution is predicted from this equation under circumstances where this is supposed to happen. The thermodynamics says this has to happen. You put it in this equation, you see that this is happening. So, something is missing. What is the missing piece? Well, it is very simple. You can look at this picture. This is what Hillard figured out first using his discrete lattice model, which was later incorporated by Kahn into a continuum model. We will see what his incorporation is. What is missing in this kind of picture is that the system is supposed to do this because it does not want to have AB bonds. There are still AB bonds because you have A rich region, you have B rich region, wherever they meet there are going to be AB bonds. Okay. In this case there are lots of AB bonds, it is filled with AB bonds which are supposed to be costly. That is the reason why the system is supposed to phase separate. In other words, the energy associated with the formation of the interfaces. What are interfaces? Here wherever AB bond forms, that is the interface between A rich region and B rich region. So, the interface related free energy is what is missing in this picture. That is the reason why we are getting inconsistent, because the making AB bonds cost the system energy. That information is nowhere here in this model. Because that is missing, the system does not realize that just because diffusivity is negative does not mean that it will do this, because if it tries to do that, the interface formation in terms of AB bonds will increase the energy, so that will stop it. Okay. So, there is a lower limit to how fine can this phase separation be. Okay. We know from experimentally it is of the order of 100 angstroms, and that is determined by the interfacial energy. That interfacial energy is missing in the model, and that is the reason why it leads to this kind of inconsistent results. This is what Hillard figured out using his discrete lattice model, and then Kahn tried to incorporate that interface related information into this equation and modified it. So, this is Fick's second law, which is really not a correct name, or this is the classical diffusion equation, which is my preferred way of referring to this equation. Okay. So, this is classical diffusion equation. But in this classical diffusion equation, any interface related information is missing. What Kahn did is to put the interface related information. In fact, he incorporated incipient interfaces. When the system is trying to undergo phase separation, A rich regions, B rich regions, whatever be the small A rich, B rich regions that are forming, and however A rich and however B rich they are, the interface between such regions, how much energy do they cost to the system, was incorporated by Kahn. Now, before deriving this final non-classical diffusion equation or that Kahn derived, which is known as the Kahn-Hilliard equation, we need to do some amount of mathematical background to understand how the equation is derived. So, I am not going to derive this equation today. We have to go through several lectures and understand several mathematical concepts before we can actually derive the expression. but we will do it as part of this course. That is one of the major chunks in this course to derive this non-classical diffusion equation. But for now I am just going to show how this equation looks. This equation, which incorporates the interface information, looks something like this: m by nv g double prime del squared c by del x squared. So, this first term is the same as this equation, minus 2 times a quantity called kappa del power 4 c by del x power 4. This kappa is known as the gradient energy coefficient. This equation we have written is one of the most important equations in phase field modeling. It is a non-classical diffusion equation. You can see why it is non-classical. The classical diffusion equation would have been this: we have added a higher order term. It is also highly non-linear, you know, it is del squared c by del x squared, now you have del power 4 c by del x power 4. This equation in materials literature is known as the Cahn-Hilliard equation. Okay. This is not the only way in which you can make this equation non-linear. For example, you can also add a polynomial in C to this term. That is also done. We will look at equations of that type also. That is known as the Alencon equation or reaction diffusion equation. But we are going to do the Cahn-Hilliard equation first. Now, to see how this equation can be derived, okay, because this equation is derived by incorporating into the thermodynamics the information or the energy associated with interfaces, and that makes the free energy no longer a function of composition, but a functional of composition. So, we need to understand what a functional is. And if you have a functional, we said that the chemical potential is nothing but the derivative of free energy with respect to the number of atoms of a particular type. Dou G by dou Nb will give me mu B. Now, if this is no longer a function, you can't take the derivative of this type. You have to take what is known as a variational derivative. So, we need to understand some concepts of variational calculus, because you can't do ordinary calculus anymore. So, by extending the idea of free energy, by incorporating the concentration gradients, because what is an interface? Interface is a region where the concentration is changing. This is all A, this is all B, and interface is a region where the concentration changes from A to B. So, that information has to be incorporated. So, the free energy becomes not just a function of composition, but also its gradients. If I do that, then the free energy function becomes free energy functional. If it is a functional, then I cannot take ordinary derivative, ordinary calculus does not work, I have to do the variational derivative. Then if I do the variational derivative and get the chemical potential, after that it is the same way. So, you go back to this equation and put this chemical potential and derive the evolution equation, then you end up with the so called non-classical diffusion equation or the Cahn-Hilliard equation, which is what we will do in the second part of this course. But before I do that, after we write this equation, we are also going to try to solve this equation, both the classical diffusion equation and non-classical diffusion equation, using some finite difference and spectral techniques. For doing that, it is easier to write the scripts in a program called Octave, which is an open source equivalent of MATLAB. Okay, so, the scripts that you would write will also work in MATLAB if you have access to it, for example, but it is not necessary. You can download and have Octave installed on your Windows or Linux computers. So, I have a Linux machine on which I have installed Octave. So, we are going to have some practice sessions with Octave. We are going to plot things, we are going to try to write small scripts which will help us solve equations of this type. And once we have some familiarity with Octave, which is what will be done in the next part of this course, we will come back, we will do all the basic mathematics that is required to derive the Cahn-Hilliard equation, we will derive that, and then again go back to Octave to solve the Cahn-Hilliard equation and look at the solution and so on. So, this is going to be the major chunk. So, in this course we are going to look at the material science, mathematics and computational aspects. So, till now we have looked at the material science aspects. We are going to start with the computational aspects. We will come back to the mathematical aspects a little bit later. Thank you.